And I'm not just talking about plants and vegetables and fruit trees and it's everything. I mean, the whole thing is about soil. Your every moment of your existence is completely dependent on soil. Not just dependent, I mean, literally, your body is made out of the same thing that is in the soil. I happen to have a little bit of soil right here. Here's a little chunk of soil I just pulled out. And what this is made out of is exactly the same thing that you're made. I mean, every atom in your body has been through the soil system billions of times already. I mean, the fact that you are not soil at this moment is a temporary condition, folks, and it's almost over. And I don't mean this talk. I mean, we're just here. Like most of the time, we're like soil, and we're up here. Hey, this is pretty cool. Before you know it, it's over. And 70, 80 years. What's that? It's just a flash in the history of the Earth. We have 4.5 billion-year-old Earth, and you're just like here today, you're just gone tomorrow, and yet here we are, amazingly together in this strange electronic sort of universe. But we are here theoretically, all of us. You're real, I'm real, and we're here together at this moment in the history of the cosmos, at this particular time in the history of the cosmos. And we're here together. And at this time in human history, we know stuff about how this works. We know stuff about what we're made out of. And that wasn't true even 150 years ago. Like, it's just like a remarkable time to be together, to be able to talk about this amazing subject. Soil, we have a big chunk of soil here. Look at this thing. I mean, just look at it up close. It's just like complicated. Look at all those holes in it and stuff. All of that was naturally derived, all of that structure from roots and burrowing insects and worms and left behind. And this is sculpted by organisms. I mean, I don't even know this, but every atom in your body was once inside of a rock. Here's a rock. I just happen to have one here. And there's this kinds of rock. And because what is a rock made out of? A rock is made out of the elements in the periodic table, right? There's 118 different elements in the periodic table. That's what everything is made out of. Everything you've ever seen, everything you ever will see, every person you've ever seen, every rock, every handful of soil, all of it, everything you touch is made from those elements. And we're all made of those things. And they're mostly are in rocks. All a rock is a collection of minerals. You can see the different colored crystals in there. Those are different minerals, and minerals are made up of different collections of those elements in the periodic table. And so a rock is just a bunch of chemicals. Now, I don't know if you know this. I mean, most people never think about any of this stuff, of course. And they ironically go to their graves, having never once considered the reality of what soil is. I mean, soil is reality. It's the reason we're here. And, it's an indisputable fact that we are made from the same thing. And all soil is sort of decomposed rocks in a way of thinking. And I don't know if you know this, but rocks dissolve in water. And most people, of course, just can't even fathom that, because you could have this rock and put it in your garden for the rest of your life, and it would look exactly like this by the time you get to the end of your life, because in our view, they just don't dissolve. We can't see it, so we don't believe it because we can't see it, but we don't live long enough. And actually, rocks dissolve rather fast at the surface of the earth in water. I happen to have a little bit of water right here. I mean, if you don't believe me, all you're going to do is today at lunch or at dinner or whatever, and take a little bit of table salt. Here's some sodium chloride in here, which is just kosher salt. Take a little bit of that, put it on your hand, and then lick it. Dissolved. Sodium chloride is a mineral, and this is a mineral that dissolves really fast. And some minerals dissolve fast, like salts, and some minerals dissolve slow. And they all dissolve, though, eventually in water. And in geologic time, pretty fast, actually. I mean, here's this rock, right? And I'm just gonna put a little water there. Ready? You ready for this? Okay, we're gonna put this on this one. A tiny bit of that rock just dissolved. A very, very tiny amount of it. And the first thing to dissolve out of a rock are the salts, because they're most easily dissolved, right? And that's sodium chloride. And a tiny bit of sodium chloride just fell down on this table down here, and it's going to evaporate, and there'll be a tiny bit of salt there, and then we'll wipe it up with a paper towel at some point, and we'll throw it in the trash, and the trash will end up out in a pile somewhere on the surface of the earth, and it's going to rain at some point, and that salt is going to dissolve again. It's going to move down a little bit, and then it's going to precipitate out because it dries, and then it's going to move down every time it rains, and pretty soon it's going to get all the way down into the soil. Sooner or later, everything, just look around the room. Just look around your room. Everything you're looking at right now, sooner or later, is going to end up in the soil. Just pretty quickly, actually, pretty soon. The building you're in is either going to burn down or they're going to tear it down, and they're going to put it in a big pile, and then it's going to start rotting away. And when that salt moves down into that soil, and then it rains, it goes a little deeper, and pretty soon it gets to the water table, and it's in the water table, and the water table is connected to the little creek that's flowing, which goes into the bigger creek, which goes into the bigger creek, which goes into the giant river, which goes into the huge river, which goes into the ocean. And that's why the oceans are salty, because the salts dissolve out of the rocks and they end up in the ocean. And the next thing to dissolve out of a rock is the molybdenum and the calcium and the phosphorus and the potassium and all those are nutrients. That's where nutrients come from. They dissolve out of the rocks. And where do they end up? In the ocean, sooner or later. And that's why they're sharks. Because the nutrients end up in the ocean so that phytoplankton can assemble them, tiny little plankton, using the energy of the sun, make these little things, and they get eaten by zooplankton, and the zooplankton get eaten by a little fish, and the little fish gets eaten by a bigger fish, and pretty soon it's a shark. And that's the nutrients that dissolved off of the earth crust into the ocean. And that's why there's life in the ocean. Okay? So in between that time, and the thing is before we go any further, look, here's a different kind of rock. Look at this rock. All these rocks, I mean, look at this. This is a metamorphic rock. It used to be a mudstone. And each one of these are different kinds of chemicals. And so the soils that form from them have different nutrient qualities, different properties, because they're from different kinds of rocks. So the soil that forms from the rock is sometimes related very closely to the rock that is underneath of it. Not always. In fact, 70% of all soils are from transported geologic materials, meaning from wind or floods or something like that. Only about 30 or 40% actually form from the rocks that are underneath of them. And it's like, whoa, what are you talking about? Well, hang on, we're getting there. Okay, I just wanted to kind of cover where these nutrients come from. And what soil is, write this down, soil is transformed geologic material. I know. It's too bad. It's Saturday. You're in school. All right. So transformed geologic material. And it's transformed because of dissolution, because a rock is actually quite unstable at the surface of the earth. This rock was made at high temperatures and high pressures from molten rock down 100 miles down from where you're standing right now. You go down far enough and you're going to hit rock. You go down far enough and you're going to hit molten rock, between 10 and 100 miles, depending where you're on the planet Earth, okay? and huge pressures and very high temperatures are forcing these chemical reactions to happen. And then when this stuff cools, it leaves behind these crystals. And we could go in, you could see those big honking crystals in there, right? And so then this thing somehow either gets to the surface by uplift from continental plates lifting up and comes in contact with the surface of the earth. And at the surface of the earth, there's water, and it's very low pressure, and it's not hot, and it's low pressure. And so these things are actually quite unstable at the surface of the earth. And so they start to dissolve, or what we call in soil science, weathering, like weathering away. And when they weather away, they release nutrients. And that's where the nutrients come from that are every piece of food that you put in this hole every day of your life. Those nutrients dissolved out of rocks, and plants have figured out a way to take up the nutrients to build the tissues that are in it. I even look at this. Look at this here's a little dried rose. This was once a bunch of rocks that dissolved, and the plant figured out a way to build these tissues out of those minerals. Look at this. Here's a bone from a chicken bone. Mostly, what's that made of? Calcium. Where did that come from? Dissolved out of a rock, and a plant took it up, and then the bird was fed food or pecked at the ground and it ate bugs that ate plants. And that's how every atom in your body got that way. I've never done this before. Gotta do this. Yeah. Okay. So you kind of get that? So what soil is transformed geologic material. But what it really is somewhere between all of the nutrients being locked up inside of a rock and complete dissolution out in the ocean. Somewhere in between the ocean and rock, these rocks fall apart into different sized particles of sand, silt, and clay. And the coarseness or the texture of the rock begets the sandiness, siltiness, or clayiness of the soil that forms from it. So that's like fundamentally, I think it's so important for you to understand that, because most people just don't. And they don't understand that they're part of the earth. And every atom in your body, sooner or later, and I would argue pretty soon, is going back to the earth. And it has been recycled thousands and thousands, billions of times already, right? And even some of the elements that are in your body sooner or later are going to be back into the melt of the rocks and come up out of volcanoes yet to be even born yet. It's a long time. It's another 4 billion years out there. Although I just did hear a disturbing fact that, well, we don't have to talk about 1 million years from now, it's going to be too hot and there'll be no more life on the planet. But don't worry about that. It's a long time from now. In the meantime, we're going to garden and we're going to have a great time because we're here, and we're so lucky to be here at this moment to actually enjoy life on the planet Earth. So we've talked about what soil is. It's transformed geologic material, that all the mineral nutrients, they dissolve out of rocks. And I don't know if you know this, but there's over 20,000 different named soils, just like plants and animals, right? You all know about the Linnaean system of categorization of plants and animals. Well, in soil science, in the past 150 years, we figured out where all these different soils are. And we'll talk about that in just a second, but I happen to be in this awesome lab here, and I'm going to take you over just to look just briefly, just to see these different monoliths. What these are is these are actually taken from the earth, intact soils samples at depth. Here's the surface of a soil called amity, and actually mounted like a specimen here. And you can see that there's some organizational features to it. Like near the surface, it's usually darker because that's where the organic matter accumulates. Because organic matter, when it rots away, becomes black stuff. And down here, the further down we go, the less weathered the soil or the materials are. So this is the subsoil. So you got your topsoil and your subsoil, but look at all these different soil types. I mean, this one over here is called Jory. This is our state soil in Oregon. I know. Can somebody just Google what state soil in Washington is and let me know, because I can't remember if I'm supposed to know that. I think it's something called. Anyway, so 20,000 different named soils, and here's just a few of them. Right, these are important soils that happen in Oregon, and we teach our soil science students that stuff. Come back over here, and the reason there's so many different soil types is because there's so many different kinds of rocks, and different parts of the planet make different soils, and so they have different properties. So, so before we go on, before we actually get to the slides, we have to talk about one more thing, a super important thing, and this is like fundamental information about living on the planet Earth as a human. Okay, so pay attention. There's something else in soil. Soil isn't just rocks or small rocks or whatever. It's also organic matter. And you can see that was a plant that lived in the soil. Here's the roots. The roots are also organic matter. So organic matter above the surface of the soil and below the surface of the soil. And plants, what plants are mostly made out of, and I wish I could interact with you a little bit more, but it's probably not practical the way we have this set up for me to ask questions, because it'll take a while to get an answer from you. But what plants are made out of mostly is not minerals. They're mostly made out of carbon, and they're actually mostly that's water, but the water is, it's kind of in the cells, but what actually the plant is actually made out of mostly is carbon. Same for this little rose right here, right? Mostly made out of carbon. And where does the carbon come from that makes up a plant? It comes from the atmosphere, and you probably already know this. You probably read this. You probably got an A on it in an exam or something. But plants, you probably know this. You know that plants take in carbon dioxide and give off oxygen. Most people know that these days, because 100 years ago they didn't. 100 years ago, people didn't believe in carbon dioxide, okay? Because they couldn't see it. And yet we know for a fact that this is made out of carbon mostly, that comes from carbon dioxide from the atmosphere. So plants, they don't breathe carbon dioxide. They eat it. Plants eat the atmosphere. Write that down. Plants, I can see you. Okay, very good. Excellent. Thank you, South Bend, Ocean Shores. Excellent. Plants eat the atmosphere. They eat the atmosphere, and they take that carbon dioxide, two oxygens and a carbon, right? And they take that in and they take it apart, and then they put it together into wood or leaves or petals or roots or whatever a plant, spinach leaves, flowers, seed, all of that is put together from disassembled carbon dioxide. Carbon dioxide taken apart and then put together into those different tissues. And so, kind of in a not exactly scientific way of talking about it, but in a way, this rose is compressed air. I don't know. It's kind of a way of thinking of it in a way that's not really accurate, but conceptually, right? And so that carbon dioxide has been taken apart and put together into a rose based on the DNA instructions that are captured. The information is stored in information molecules that themselves are made from dissolved rocks. Okay? It's pretty trippy. Once you start really kind of figuring this out, you realize, whoa, everything is made from dissolved rocks. and the instructions to make a rose are contained in the DNA inside of a rose, so it can eat the atmosphere, take apart carbon dioxide, then make a petal out of it, right? Kind of amazing. So to take that apart and put it together into a rose petal requires work. I mean, how do you take something apart and then put it together without doing work? And in order to do work requires energy. To make this thing requires energy, and it's a chemical reaction called an endothermic chemical reaction. That's a chemical reaction that requires energy input. Like to cook an egg is an endothermic chemical reaction. It requires energy input to change the egg from a liquid into a solid or a semi-solid, right? That's an endothermic chemical reaction. So, gardeners, let me ask you, where does the energy come from for a plant to eat the atmosphere to turn itself into a plant? Just point the right direction, please. The sun, right? The sun provides that energy to the planet. 93 million miles away, there's a ball of fire out there, a nuclear reaction, a nuclear reactor, I should say, that's giving UV radiation. There's a giant, it's a star. The nearest star is giving UV radiation to this planet. Then that UV radiation is tiny little sliver of it hits this tiny little speck of dust called the Earth. The rest of the UV radiation goes off into space, but this tiny little bit of it hits this planet. And plants have figured out a way to capture that energy, to tear apart the atmosphere and turn it into a rose. And that really, really is happening. That happened here. And this is carbon from the atmosphere and energy from the sun. In fact, so 93 million miles away, there's UV radiation coming to this planet in the form of photons, which we now know what those are because we can measure them scientifically. We've done experiments in the previous era so we could have this conversation about how things work. And those photons, they hit part of the chloroplast, and in there's a special structure in there. Then that an electron is kicked up into a higher orbital, and when it drops down, it releases a tiny bit of energy, and that energy is captured in a molecule called ATP. Don't worry about ATP. And that molecule has the energy of the sun in it. And it can be instructed by the DNA of the plant to say, okay, go over here and tear apart this CO2 molecule. And it releases that, and it tears it apart. And now another one comes in and says, put it back into the shape of a petal. And the instructions to do that happen. The roots are going down on the ground. The leaves are coming out. All that stuff is happening because of energy from the sun in an endothermic chemical reaction called growing. Okay? And that's why plants grow. And you can't farm in the winter. I mean, you can grow some cover crops, but because there's not enough energy from the sun, right? That's why we grow stuff in the summer. In the northern hemisphere, it's when we in the southern hemisphere the other time, but still it's the energy of the sun. So the thing is the energy of the sun is in this rose. At the time that the carbon-to-carbon bonds that are formed are the energy of the sun at the time of photosynthesis is in this rose right now. And that's what food is. That's why you eat vegetables, is to get the mineral nutrients that are in them, which we haven't even talked about yet, other than that we know where they come from, dissolved rocks. But the nutrients that are in here, and so is the energy of the sun. Think about it. Look at the blinking of my eyes right now. Every blink of my eyes and every blink of your eyes is the energy of the sun that was captured by photosynthesis by plants that lived in soil. And now we eat that, And we have an exothermic chemical reaction inside of us that releases the energy so that our hearts can beat, so that our eyes can blink, so that you can listen to this sentence that I'm speaking to you, so that by the time you get to the end of this sentence, you still know what I'm talking about. That's all energy from the sun that allows for that information to be stored in your brain. You're just a big bag of wet rocks. And it's almost over, folks. And I don't mean this talk. And you are an expression of sunlight energy, man. I mean, really, you are an expression of sunlight energy. And every moment of your existence, that's the facts, Jack. I mean, that's actually what's going on the planet. Plants have figured out a way to eat the atmosphere using the energy of the nearest star, and they pull up nutrients at their roots in the form of dissolved minerals. That's what fertilizer is. What are you putting on your garden? Potassium, phosphorus, palladium, all this stuff, right? Where'd that come from? Dissolved rocks. And if you're an organic farmer, like I am, all you're doing is putting on fertilizers that are special kinds of organic matter, like, seaweed, kelp meal has a lot of potassium in it, or feather meal has a lot of nitrogen. It's different kinds of organic matter. And then you're feeding, I don't know if you know this, but in a single pinch of soil, like this pinch of dead looking soil here, a single pinch of soil has over 1 billion living organisms in it. 1 billion living organisms in this pinch of soil. Even this dried out piece of soil that's been sitting in this laboratory for 10 years. It's got 1 billion living organisms in it right now, and they're just waiting for it to get wet. And look, I'm going to wake it all up. Oh my God. It's like heaven just happened in this pinch of soil. These guys have been waiting for moisture for 10 years, and they're waking up, and they're coming out, and they're going to start doing their thing. You know what they're going to do? They're going to eat organic matter. And what is organic matter? Carbon from the atmosphere, energy from the sun. That's what they eat. You want to know what the answer is? Doesn't matter what the question is. Do you want to know what the answer is? The answer is add organic matter, gardeners. Because when you add organic matter, you're adding energy from the sun and carbon from the atmosphere to the bugs that live in the soil. There's over 1 billion living organisms in the soil that don't even know there's a sun. They're underground. They're just waiting for stuff to die so that they can eat them. And they're just waiting for stuff to die, folks. That's all I'm saying. Don't need to go any further than that, because it won't be long. It's almost over. I don't mean this talk. And back to normal. Don't worry. It's back to normal. So these billions in a single pinch, and you might think 1 billion in a single pinch. It's not just 1 billion of one kind of thing. Literally, there are tens of thousands of species in here right now. 99.99% of which we don't even know who they are or what they do. We know they're there. We can count them. We can count them using DNA technologies that didn't exist 20 years ago. And we can probably say we know an order of magnitude more of them than we ever knew before. And what are they doing down there? You know what they're doing? They're eating organic matter, and they're tearing it apart, and they're releasing the chemical nutrients that are in the organic matter that came from a rock originally, and they're making it available to the next generation of plants. And when they do that, now the plants can go above ground, gather energy from the nearest star and carbon from the atmosphere, and build more soil, build more roots, which go down deeper, and you know what happens to a plant? Eventually it dies. Imagine the roots going down deep, and now it dies. And now it's pumping carbon and energy into the soil. And that happens, and now there's more bacteria and fungi down there. And because of that, there's more efficient processing of minerals and chemicals and energy and nutrients, so that more plants can grow. They're capturing more sunlight energy and more carbon from the atmosphere. And that's what soil building is. over time. That's why there's surface soils, right? Topsoil. Why is topsoil dark? Because it has more organic matter. What is organic matter? Carbon from the atmosphere and energy from the sun. And the more of that there is, the more biota is in there. And the more biota it is, the better it is to grow plants. And the better it is to grow plants, the more carbon and energy comes into the system, and the more biota and deeper and deeper. And pretty soon that's called a type of soil called a mollisol, which is a good garden soil. And you've probably tried to grow in soils that are not really great, and you probably had gardens that are really great because they're better soil. They're better for growing food because they have more biota in them and they have more organic matter. So what's the answer? 1, 2, 3. What's the answer? Add organic matter. One more time. What's the answer? Add organic matter, because when you add organic matter, you're adding carbon from the atmosphere and energy from the sun that makes the thing more biologically active, right? You kind of get that a little bit? Okay, so we had to, we didn't had to, we were lucky enough to talk about something real, okay? All of that, that's reality, man. Everything else, look, there's a star that's giving UV radiation to this planet. Rocks dissolve in water. Plants have figured out a way to take up those mineral nutrients and use the energy of the sun and eat the atmosphere to get the carbon. And that's what it's all about. That's what's going on planet Earth. And everything else is a sideshow. All the stuff that's going on in your head right now, that, it's crazy stuff going on. And yet it's all from these basic principles. And I really, really wanted to kind of drill into that. So we are going to go to some slides now. I'll tell you the slides, where are they? What are my slides? Okay. Slide 1. Slide 2, you ready for it? It's all about soil, okay? Okay. And everything I was just saying is this slide, okay? And I needed to get there before I could even show you this slide. And now you kind of know what soil is. It's probably pretty hard for you to imagine the length of time. It's hard for me, and I've been thinking about this for 24 years. This idea of how long it takes for soils to form. I mean, hundreds of thousands of years for soils to form from rock. So the rest of this, a few slides here might be helpful because we're kind of going to review. So look at here. So what you're looking at here are a profile view, meaning if you dug a hole and you went and you looked at the wall of soil, okay? It's called a profile, soil pit. And there's 12 soil orders. I promise I'm not going to make this super boring about all that stuff. It's because, well, it is not boring. It's totally fascinating, but we don't have enough time for me to really get into it. But there's 12 different soil orders. According to the USDA, we've categorized the soils on the planet Earth, and there's 12 of them. There's other systems. There's native systems. There's the FAO system, your Japanese system. There's a bunch of different systems. But I'm mostly just talking about the USDA because it's the one I'm most familiar with. And remember I said there's 20,000 different named soils? They all belong to one of the 12 soil orders. Look at the one on the left here. It's called an aridisol. What do you think that means? Aridisol, right? Dry soil, right? Not a lot of rain there, right? Do rocks dissolve in air? No, they dissolve in water. So do you think in a desert soil like this, there's a lot of nutrients being released from the rocks? No. So is it harder for plants to grow there? Yeah. So what do you have to do? You got to look like this if you want to live there. A plant that has adapted to dry soils and not a lot of nutrients. And look how this is a very thin soil. That's it. It's about 12 inches thick. The whole soil is. And why is that? Because it doesn't rain enough for it to go any deeper. The water itself doesn't go any deeper than 12 inches. So that's as deep as the soil can form, right? And if you look here, do you see this let's see this layer here. I hope you can see my cursor. Maybe you can. Yep, this layer right here. You know what that is? Salt. What's the first thing to dissolve out of a rock? Salt. And how far does it go? Only as far as the water goes. It never gets to the water table. And so then it dries out. Now there's a layer of salt here. So now you've got a really salty soil that's really thin, and there's not a lot of other nutrients around. And that's why you got to look like this. And that's what a native plant is. Native plants have adapted to living in the subsurface soil conditions as well as the above ground, but really a lot of it has to do with what's going on below ground. Even in this, look how light colored this soil is. Can you see how light it is in color? Not a lot of organic matter. Why is that? Because organic matter slowly accumulates in a dry place, right? And so it's just a different kind of soil, and it's really hard to grow food in soil like this. And look over here look below it. You see below it? Those are the rocks from which it formed. So there's this transformed geologic material that's about a foot thick. You could count this salt as part of the soil because it's transformed geologic material. So this whole soil profile is maybe 18, 20 inches deep. That's just one of the soil types. And it belongs to the area. So look on the right-hand side here. This is what you want. Even you know this without having ever studied soil science ever before. You can look at it and say, wow, look how dark that is. That's going to be good soil. You know why? Because you were taught that by your grandparents probably. So, oh, the dark soil is good, right? And that information has passed on since before people could even use spoken language. People knew how to identify good soil for food, for resources. You know, think about that. 100,000 years ago, people were like going, oh, this is good, right? Because they actually, I would posit that ancient people were probably more attuned to soil than modern people are. Modern people don't even think about any of this stuff because they don't have to, because the invention of agriculture allows for specialization. And we're all specialists. Hey, I know you guys are all gardeners and stuff like that, but you're not growing all your own food, you know? Somebody else is. Experts are. And all of you are experts at other things because of the invention of agriculture. Some people became the experts at growing food so that other people could become heart surgeons and stuff like that. And that is why, I mean, and think about this soil on the right is called a mollisol, which means to mollify is to soften. Look at this is in feet. This is 2 feet thick of what we call topsoil, which is an A horizon, which is, and all that is from organic matter, from roots. Plants grow roots that push carbon and energy into the soil, and then they die and they leave it behind. And they just do that over and over and over and over and over and over and over. And pretty soon you got what's called a mollisol. And these are the most important agricultural soils on the planet. And it's the reason you're just sitting there playing hooky on Saturday and having a good time, is because this country has more mollisols than any other country on the planet Earth. Look at, here's an iridisol. Here's an inceptisol. An inceptisol, look, there's some dark stuff, but look at these rocks. This is like Washington soils. A lot of them are like this because of old glaciers that pushed the soil and the rocks together. And if you want to do agriculture, you got to dig all these rocks out first. And once you've dug them out, there's not a lot of soil left. And this is 1/3 of the Earth's ice-free surface. That stupid phone's ringing at me. 1/3 of the Earth's ice-free surface is this kind of soil. 1/3 of the Earth's ice-free surface. And another third of it, look up here. See this? These are called the gelisols. These are the frozen soils. So like half of the planet isn't really suitable for growing food crops, you know? Something like that. And in this scheme, look at this. See the green here? This is the mollisols. Look where the mollisols are. Look, we have The United States has more mollisols than any other country on the planet Earth, except one maybe, which is Russia. And in particular, the Cold War was all about they who had the agriculture. And those who have the agriculture have the advanced technological societies to build intercontinental ballistic missiles. It's all about soil. Really is. I mean, certainly there's human invention and all that, but look at where the troubled spots in the world are, where the iridosols are, right? Where the entosols and where the inceptisols are, right? I mean, this is what the hot war is all about. Look at, here's Ukraine, all right? I mean, these are the most important agricultural soils on the planet Earth for Russia. I mean, this is what it's about. And just kind of throwing that out here, you know, what you're looking at here is a map of political power. And once you see this, you can sort of start to understand the geopolitical struggles that are going on. Who thinks about this? Do you think any of your elected officials know anything about soil? This is a map of political power. And if you showed this map to your political leaders and they didn't know it was either soil or a map of political power, I'm just saying they have no business having the political power because they don't understand what's really going on the planet Earth, okay? Or they do and they just don't care. There's that too, I suppose. And look, here's the Sahara, right? I mean, these are the difficult places to live. And in the tropics, you may think, oh, the tropics, aren't they really great? No, it's so wet and so hot there and so much vegetation there that all of the nutrients and the soils are really old. All the nutrients have gone out and become sharks. And you're thinking, yeah, but what about the plants? They're recycling those nutrients feverishly, recycling them above ground. That's why the jungle looks the way it does, because nothing escapes that cycling above the ground. So most of the nutrients are being recycled above the surface of the soil in the tropics. And that's why it's so diverse there, because everything is being saved and captured. And like the minute a leaf falls in the tropics, before it hits the ground, it's being ripped apart by an ant. And before that ant tucks into bed that night, it's being eaten by something else, which poops it right out on the roots, which are above ground. And then the plants suck up the nutrients and it never gets into the soil because the soils there are quite poor. Okay, and that's the tragedy of cutting down the tropics for wood and to grow some animal meat on for a while, is that the soils never, ever, ever, ever come back, and the tropics and the jungles never, ever, ever come back because they formed under conditions that no longer exist. And I'm not going to go on and on about, because we got to talk about what matters to you, but I just wanted to get you this kind of global sort of perspective of what you're doing in the garden is directly related to this stuff. So keep doing what you're doing. You're doing a good thing. You're growing, you're improving soils. How do you improve soils? What's the answer? Add organic matter. How do you improve soils? Minimize disturbance. Because what plants are doing, I think this is worth stopping to talk about just for a second. What plants are doing is they're sculpting the soil to make it better soil for plants. Remember I showed this at the very beginning? This, look at, those were all roots that were in there. That was a root that went in there. And then it got bigger. And then it died. And then it went away. And, you know, we got to talk about one thing about organic matter and where does it go? Where does the dead stuff go? It goes back to the atmosphere. Look, here's a piece of wood from Brazil. This was once a tree. And if I get this tree, this piece of wood, to 451 degrees, you know what happens to it? I overcome the activation energy necessary for the chemical reaction to happen, called burning. And when it burns, look, that is the energy of the sun. That's the energy of the sun that's in the wood, and I've got it to 451 degrees, and now it's continuing to, ouch, it's continuing to overcome the activation energy necessary. Watch this. I have a demo. Let me do a little quick demo. I think it's worth doing. Hold on. I live for this, so let me live. Close-up desk. Boom. Let's go over here. Look at this. It's coming. Look, paper towel. What's paper towel made out of? Wood. This was once a tree, right? There's energy in this wood, and you know it because if I could get it to 451 degrees, what happens to it? It burns. And that's an exothermic chemical reaction that is releasing, ooh, look out, that is releasing energy from the sun, up from the wood, and it keeps burning until it goes away. Where is this paper going to? Somebody put it in the chat. Where is the carbon going to? You might think, the atmosphere, the carbon, yes, the carbon is going back to CO2. But look what's left over. What is this stuff? What is that stuff? Not carbon. The carbon goes back to the atmosphere. These are the minerals that were taken up from the dissolved rocks. And that's why you eat. The same thing happens inside your body, but at a lower temperature. Instead of having to get it to 451 degrees, we have bugs inside of our, look, there's a hole here and there's a hole down here, and there's a tube going through your body. And the bugs, the billions in a single pinch that are in soil, are inside of that tube. And you're feeding them. And what they do, what bacteria do in the soil and in your gut, is they ooze out enzymes. And enzymes are catalysts that create this chemical reaction, but at a lower temperature, at like, say, 97.5 degrees or something like that. That's happening inside of you, burning. Look, how do you get a fire to burn hotter, folks? You add oxygen. Okay, everybody ready? 1, 2, 3, oxygen in. What comes out? CO2, water vapor, heat. Oxygen in. CO2, water vapor, and heat. Heat, you can feel it on your hand. You can see the water vapor. Right? That's the same chemical reaction as happening inside of you right now, because of the bacteria that live in your gut that lower the activation energy using catalysts for that chemical reaction. And what's left over after you eat the food and exhale the carbon? Nutrients, mineral nutrients. Every cell in your body is made from a phospholipid bilayer. Phosphorus, key macronutrient. That's the P and the NPK. That's why you got to eat. That's what plants are made of. They're made out of phosphorus because they have cell walls that are made of phospholipid bilayer. And where does that come from? Dissolved rocks. And how do they make a phospholipid bilayer? By the instructions in the DNA to do it. So, and the same thing is happening in the soil right now. The bugs are in there. What are they doing? They're waiting for organic matter. And what do? They use enzymes to lower the activation energy necessary for the oxidation reaction called burning to happen. And what leaves the soil? CO2. What comes out of a compost pile? You ever notice how a compost pile goes away? Just like in a fireplace, when you're burning wood, what does it do? It goes away back to CO2, water vapor, and heat. What's left over? Ash, mineral ash. That's what compost is. It's a fire that burns at about 140 degrees because of the bacteria that use chemicals to have it happen at a lower temperature. And what happens to a compost pile? It gets smaller because the carbon is leaving. And what happens to compost as it gets smaller? by volume, there are increased amounts of nutrients in it. So when you put it on the garden, it's already got higher concentration of mineral nutrients in it. Plus, it's got all that biological activity. And so you're stimulating biological activity in the soil so that your plants can grow in it. Dang, okay? You follow me a little, tracking me on that? I know it's a lot. I know it's like 10:30 in the morning, or what is it? 10:30. God, I gotta get cracking here. All right, I'm gonna show you just a couple more things. And then I'm gonna show you some online stuff that's really good. So where am I? I guess I stopped there. God, I'm got a ways to go. Let's see if I can skip by all that stuff. It's really cool. I'd love to show you it sometime. And here's this, here's an image of a tiny little piece of soil. This is like 0.5 millimeter by 1 millimeter. And this is, I think, really important slide for you to like get in your brain. Soil is habitat. And its habitat, it's the most diverse habitat on the planet Earth by any measure. Okay, by any measure. A single pinch has over 1 billion living organisms, representing tens of thousands of different species. And what are they doing? They are using enzymes to recycle carbon, energy, and mineral nutrients and make them available to plants so that plants can gather more energy from the sun and carbon from the atmosphere to feed the bacteria and the fungi so that they can release more mineral nutrients. But plants do this amazing thing. They go into tiny spaces and then they get bigger. And when they do that, they're using the energy of the sun to sculpt the soil. And this is such an important concept, you guys, is that what you're after as a gardener is you're trying to make the habitat as diverse as you can. And the way to do that is to just leave it alone as much as you can. Disturb it as little as possible. Now, I'm not saying you eliminate that because it's, you're gardening. You're not running a forest. You're trying to minimize diversity because you want corn in one place. So you have to sometimes disturb the soil, but you don't have to turn it into dust every year, okay? Because look at this. I don't know if you know this, but small pores hold water against the force of gravity. Can you see that little bridge of water in there? See that? You've all done this. Take a bath tonight and say, what the hell? Why is that little thing of water just sitting there? Well, small pores, because it's called capillary force. And small pores hold water against the force of gravity, and large pores drain into the force of gravity. And so what you want in soil is you want large pores that drain into the force of gravity and small pores that hold water against the force of gravity. You want both. And so by minimizing disturbance, think about what a root is. It's a big thing that goes in and gets smaller, and then it gets smaller, and then it gets smaller, and it's smaller. And so what a root does is it sculpts large pores, medium pores, small pores, and super tiny pores. And then when it dies, it goes away. And it leaves behind a casting of the root structure. And the roots have been selected over time and responsive to the types of soil that they're in to make a wide pore size distribution. And why do you want a wide pore size distribution? Because when do plants need water at their roots? All the time. And when do plants need air at their roots? All the time. And so what they need are large, medium, small, and tiny pores. And if you just minimize your tillage, the plants do that. They sculpt the soil to make it better habitat for the next generation of plants, which makes it better for the next generation of plants, which makes it better for the next generation of plants. And that's more carbon from the atmosphere, more energy from the sun. And that's what soil building is. And that's why we're actually here, because of all that happened. The laws of physics and the biological response to those laws are the reason we are here today, is because enough nutrients were captured, enough energy was captured from the sun and stored in the form of organic matter so that we could be here. And if you look at this tiny little piece of soil, a 0.5 millimeter by 1 millimeter. And look at this little body of water between these 3 pieces of sand. This sand came from the Gobi Desert. This came from a giant flood. This came from a glacier meltout. And each one of these has a different chemical signature that's dissolving nutrients into this ocean of water. And in this tiny little ocean of water is a sea serpent that lives in here. And this thing's trying to eat these things, but these things drink the poop of those things, and these things are waiting for this thing to die so they can eat them. And there's a whole ecosystem going on between 3 pieces of sand. And who thinks about this? Hardly anyone in the world. In fact, nobody thinks about this little ecosystem except you guys and me right now in between these 3 pieces of sand. And look, way up here is a different habitat. It's aquatic, but look, it's connected to this big pore, and there's probably manure being generated by this critter that lives up in here that adding nutrients to this water. Very different chemical signature of this water than there's down here. And look at this one up here. This body of water, there's a root here, and look, there's a fungal mycelium, and this fungal mycelium is mining nutrients from this piece of sand and giving it to this root, but this root is pumping carbon into this water. This has a different pH and a different temperature to this water, and it hosts a different biota in here, which is completely different from the ones that live down here, which is completely those ones. And there are some bacteria that live in the hair follicles of this organism that might be the keystone species to the whole aggregate. And look at this big pore right here. Do you see this big space here? This is filled with air. Well, how did this get here? That used to be a root there that went in there, pushed those rocks apart, died, went back to CO2, water vapor, heat, and now this has oxygen every time it drains. Think about it. When a drop of water goes down an old worm channel or down an old root channel, what's being sucked in behind it? The atmosphere, air. When the soil is draining, the soil is breathing, and it's bringing oxygen deeper into the soil where the billions in a single pinch live, who are processing carbon, energy, and mineral nutrients. And that's what soil building is, man. And your job as a gardener is to just coax it to do that. And that's why we grow cover crops, because we want roots in the ground, right? Which sculpt the soil. And when we kill the cover crops and we put them back in the soil, they add carbon and energy to the system, which make it more robust. And so a little bit of tillage is, we're talking aggregates this big. As long as you just don't grind it to dust when it's too dry, or grind it or smear it all up when it's too wet, these soils are quite resilient. So you don't have to eliminate your tillage, but you need to be mindful of your tillage. And if you're putting in 4-inch pots with big plants, the transplanting, you don't need to pulverize the soil as if you're putting in carrot seed. If you want carrots, yeah, you really got to pulverize the soil to get a fine soil so you have seed to soil contact, but you don't grow carrots in the whole garden. So only do that to where you're growing the carrots. Don't just till the whole garden. Think about where it actually needs to be tilled, where it needs minimum tillage, or maybe where you're just going to leave it for a year or something every once in a while. And just do that. And you're adding and storing carbon. And when you rototill soils, you get more oxygen into the soil. And what does that do to a fire? It makes the CO2 leave the system because you're burning it out. And if you add, look at the room you're in right now, if you had more biological activity in there, the CO2 levels would rise. But if you open the windows, the air would come in and you could do more work. It's just, you got to think about it as habitat. Bottom line, soil is habitat. If you get nothing else out of this talk, if you can internalize the reality that this is the habitat on the planet Earth, by far the most diverse habitat on the planet Earth, that all this stuff that's going on above ground is completely relying on that. And think of your soil as habitat like this. It's a living thing. It's not just a chemical sponge, right? The only other thing I want to talk about real quick, I'm sorry we're running out of time and everything. Is that right? Yeah, we are. Is I wanted to tell you the source of this of how nutrients are stored in soil. And I've talked about these different size particles of sand, silt, and clay. And you probably learned this in your readings and stuff like that. That sand is 2 millimeters down to 0.05 millimeters, silt is 0.05 millimeters down to 0.002 millimeters, anything smaller than 0.002 millimeters is called clay. But sand is just a rock. Silt is just a smaller rock. Clay is a secondary mineral that forms when rocks dissolve and then recrystallize at the surface of the earth, which is really different than what a rock is. Remember what a rock is? High pressure, high temperature, cooled magma. Comes to the surface, dissolves, and then when it dissolves, it can, those are nutrients, but those nutrients can also recrystallize into something called clay. And clay can only get so big before it falls apart because it's rather unstable as a mineral. And so clay is a secondary mineral that forms at normal surface temperatures and normal surface pressures and is the product of dissolution and recrystallization. Okay, you know, it's kind of early in the morning, too bad. You invited me here. So let's look at what clay is. So here, look at primary minerals dissolve in water and they release nutrients, right? Nutrients can be taken up by plants, blah, blah, blah. But more importantly, the four most abundant elements in the Earth's crust, silica, iron, aluminum, and oxygen, can recrystallize into these tiny little crystals that can only get to 0.002 millimeters before they break apart. And that's what clay is. Clay is formed when rocks dissolve in liquid water and recrystallize. So in an aridosol, do you think there's a lot of clay? No, right? In a mollisol, you think there's a lot of clay? Yeah. And these little crystals are the reason you're alive, okay? It's the reason you can garden. This is it. And here's what dissolves out of a rock. Silica and aluminum, primarily. That's what rocks, there's silica and aluminum. That's what mostly what's in rocks, and oxygen. And here's these little structures, this is called a silica tetrahedron, and this is aluminum octahedron. They are what are dissolving out of the rock at a microscopic level. And silica has a certain size and a certain charge that forms covalent bonds with 4 oxygens to form a silica tetrahedron. Aluminum has a certain size and a certain charge, right? These are elements in the Earth's crust. These are elements in the periodic table. Aluminum has a certain size and a certain charge that forms covalent bonds with 6 oxygens, in this case, hydroxyl groups, but still. And they can share these oxygens to build crystals. Look, there's the aluminum, there's the silica tetrahedron that's sharing an oxygen with the next one and the next one and the next one. And they're sharing an oxygen with these aluminum octahedrons. Right? Can you see this? This is a layer. It's a crystal. And this is the edge of that crystal. And when the next iron comes, silica tetrahedron comes down, it clicks on there. And it goes, and it grows, and it's a crystal. And here's a layer. That's a 2-to-1 layer. And there's another layer, and another, and another, and another. And those can stack up until they get to about 0.002 millimeters, and they fall over. And these growing edges, they can get about so big before they break in half. And so that's the limit of the size. Now, what size pores are in between clay? Small, medium, or large? Small, right? And is water held in small pores? Yes, it is. Clayey soils hold water because of the size of the pores. A sandy soil has large pores, so it drains better, right? And a soil that is undisturbed or minimum disturbance has a very wide pore size distribution. Just saying, okay? So now look, as it turns out, there are other things dissolving out of the rocks. Instead of silicon, you can have lots of iron. And iron has almost the same size and almost the same charge, but not quite. Similarly, in the octahedral sheet, magnesium, dark colored rocks. If the kinds of rocks, like this darker colored rock has more magnesium and iron in it than does this rock, right? And so this clays that form from this can have this substitution into it. And this is it's not important you completely understand all of that, but I'm just telling you that this is the source of charge. Look at you can substitute in because of the types of rocks that are dissolving and end up with a negative charge. Here's another substitution that happens at the time of recrystallization of the secondary mineral called clay, and it has a negative charge. Sand does not have a negative charge. Silt does not have a negative charge. Clay has a negative charge. And this, when you get a soil test, you can measure the amount of negative charges, and that's called the cation exchange capacity of your soil. And the higher the cation exchange capacity is, the CEC, the more negative charge is on that soil. And what sticks to negatively charged things? Positively charged things like nutrients, like calcium, phosphorus, potassium. All those are nutrients that have a positive charge. And what do they stick to? They stick to the negative charges, the electrostatic charges that are caused by isomorphic substitution inside of the crystal and lattice work of the crystal called clay at the time of formation, based on the kinds of rocks that are dissolving out of. Some rocks can't make clay that have a negative charge. Some do. And that's the difference between an iridisol and a mollisol, right? That's what garden soil. And what sticks to negatively charged negative charges on clay? Positively charged nutrients, like every calcium ion inside of your skeleton right now was once stuck to the negative exchange complex of clay. So look at it. Look at it. Here's clay at 100,000 times magnification. Okay, it's not a ground down piece of rock. It's built up atom by atom. And this can only get so big. And look at the surface area of this. Huge surface area. A thimbleful of clay has the surface area of a football field. And it has net negative charges all over those surfaces. And that's why clayey soils store more nutrients, because they have more negative charge. Look at this clay. Negative charge due to isomorphic substitution. Look at this clay. Negative charge due to isomorphic substitution, the secondary mineral called clay. Look at this clay. Look at this clay. Look at this clay. I mean, just look at this clay built up atom by atom when rocks dissolved in water at the surface of the earth and made a giant high surface area thing called clay that has net negative charges all over it that can store positively charged nutrients. And if it wasn't for that, there wouldn't be enough positively charged mineral nutrients being stored in the soil for there ever to be macroorganisms on the terrestrial ecosystems. There'd be a lot of sharks, but there wouldn't be a lot of nutrients being stored for there ever to be plants. So I'm just saying, everybody together, 1, 2, 3, say this with me, 1, 2, 3. Net negative charge due to isomorphic substitution on the secondary mineral called clay is the reason you can garden. That's how you store nutrients. And look what's stuck to this clay. Nutrients, calcium, and they're temporarily stuck there. Temporarily until the root takes it off, right? And so you add fertilizer to put the nutrients on in the proportions that you want to grow the crops that you're trying to grow. So by putting on those nutrients, you can load up the nutrients in the type and amount of nutrients you want to grow. And that's what fertilizing is, because clay is a negatively charged thing. Oh, man. So I'll tell you, there's one other thing in soil, and you have to guess what it is. Just look at this slide over and over. One other thing in soil that has twice the cation exchange capacity of the best clay. Can you guess what that is? Just looking at this animation. Yeah, organic matter. What's the answer? Add organic matter. When you add organic matter, not only are you adding carbon from the atmosphere and energy from the sun, but you're also adding cation exchange capacity, because organic matter itself has a net negative charge in a giant surface area. And that's why it's black. So look at this. Here it is. That's a random molecule made from dead stuff. 1,000 years worth of dead stuff. Giant surface area, net negative charges all over it. Black soils have a lot of organic matter in them, and organic matter stores mineral nutrients and recycles nutrients. And that's why you want to minimize the disturbance so you don't burn out all the organic matter, because it's stored there and it's functioning to hold nutrients. I know an awful lot going down here today. I just want to show you one last slide, and then we'll get to some online resources. Here's a plant. Look, large pore, medium pore, tiny pore, dies, goes away, leaves behind a large, medium, and small pores as long as you don't rototill the shit out of it, right? And now look at this little root tip. Look, the smallest root hair. The smallest root hair you never saw. Let's zoom in on it. Look where it is. It's in a small pore. What's in the small pores? Water. Look, here's soil. Look, there's a negative charge on it. Look what's stuck to it. Nutrients. Now, this plant exhales CO2 just like you do for the same reason. Breathe oxygen, exhale CO2. CO2 dissolves in water, forming carbonic acid. You've all had bubbly water, right? And you taste it, it tastes a little acidic. That's because CO2, when it dissolves in water, forms carbonic acid, which creates hydrogen ion. And hydrogen ion is more strongly absorbed to this net negative charge than the nutrients are. Hydrogen ion is more strongly absorbed than this calcium is. So what does it do? It says, you're off, calcium. And the plant breathes and exhales CO2 more in the summer than it does in the winter because of the laws of thermodynamics. So hydrogen ion it's acidifying the soil water, which removes the nutrients because they're not as strongly absorbed as the hydrogen. And then the calcium flows into the plant, which goes into here and becomes structures that you then eat. And then you feed to the bacteria in your gut, and they get the energy and the carbon. They release the nutrients, and the nutrients go based on the DNA instructions in your body to build a skeleton inside of you. Whoa. Okay, so that's kind of where I wanted to get to today. And I do want to show you a couple of things before we go to questions and stuff like that. And I have a lot more I could show you, of course, but just take my class. So here's what I got to show you this. And I hope you don't mind me just dominating the situation here, but there's this wonderful site here called the California Soil Resource Network. Write that down. California Soil Resource Lab. Sorry, California Soil Resource Lab. And there's an app on your phone that you could download in 1 minute for free right now. Maybe the only reason to have a smartphone. Maybe the only reason to have a phone. And you type in the App Store the Soil Web app. Soil Web, just like it says here, Soil Web. And it's on your phone. And wherever you are in the United States of America, you can see what your soil type, the name of your soil is. And I'm just going to show you right now. I know, guy comes to talk to you, and then he brings out his phone. But I want to show this, how this works. You go to Get Soils Data, and look, right where I am right now are two kinds of soils. One of the 20,000 named soils. There's Bashaw under my feet, under this building right now. And Bashaw is a special kind of very clayey soil. So it has a very high CEC. In fact, this used to be a wetland. And wetlands are very high CEC soils. And Waldo is a related soil. And there's some other ones that might be here. And that's all you got to do. And then you just click on, say, Bashaw, and it'll tell you what the Bashaw series is like. And you go to this details, and I can look at the soil properties. And I can look up the CEC of this soil right here. And there it is, at depth. Can I do it? I don't see. Oh. Here's a percent sand. Here's a percent clay. At depth. You see how that works? At depth. So I know we're not going to go into this any much more, but get this app. And it's just called the Soil Web app. And it's free because the United States government, after the Dust Bowl, decided to map all of the soils in the country because it was a national security issue. the strength of the country is based on the strength of its agriculture. And protecting the soil was job one for the future. There was a time in this country when our leaders actually wanted to protect the soil because they knew what it meant to do that. And the Natural Resource Conservation Service has been doing it ever since and mapping that free to you. I know it's a long time ago when public investment in the future was kind of it was a passing fad. And yet it's free to you, and some grad students who made this for a phone app, which is really cool. But I want to show you, without going into great detail, you can install this into your Google Earth. And this is kind of nutty. And see over here, it says Soil Web over here. There's a method that I'll send that to you if you're interested, how to put this into your Google Earth. And if somebody in the chat could just give me an address that they want to see what soil, we can look it up right now. It'll be super fun. Somebody give me something in the chat, an address. Okay, that's good enough. We'll just go with and I'll copy and paste that in right now. And I'll go there, and Google Earth is just cool anyway. And we're going all the way out here. And so we're on a coast. Well, it's gonna be pretty sandy, I'm guessing. Ooh, how is that marina there? Is it pretty good? I have a house in Astoria. I don't know about this. Okay. And if I zoom in, let's go out. Here's a look at there's a farm out here, right? And look at those are the soil, those lines are showing what soils are where. There's 20,000 different named soils. On this farm is something called sea strand variant. I'm not sure what that is. It's a sea strand. And it's a muck. And it's all organic matter. See that O? An O horizon is lots of organic matter. So this is a former swamp or something that has but because it has a lot of organic matter, do you think the CEC is pretty high? Probably, right? And I think we can look at this right here. If I just go to this and we can look it up, look at C strand. There it is. Look at the percent organic matter. 80% organic matter until it gets down to about 80 centimeters. And then it goes to about half, 45% organic matter. See how that works? And let's look at the CEC. It isn't even on the chart here. It's off the charts, literally off the charts. It's over 40. And let's see, how much clay does it have? It has a lot of clay too. So it has a lot of clay and a lot of organic matter. So it's a really high CEC soil. Let's look at this soil. Oh, I think we'll go back. Let me show you a different soil here. I'm going to change a new share. And let's go to this. Can you see that? Google Earth, right? Let's look, I don't know. Well, let me just look over here. Look at the red color of these soils. This is interesting. It'd be interesting to see what that is. Here's one called Orcus. Also another histosol. These are all very poorly drained. I just want to get to a mineral soil just for fun. Here's more of an upland soil. And you can do this. Just put in your own address. Here, look at these are upland soils. Look at the color on that thing. Red. And if I look at Vista Silt Loam, which is one of the 20,000 different named soils, I hope you can see this. Let me new share. We'll look at this. Here we have Napton. Let's look at that. Percent organic matter is about 12%. It's a little bit of sand, a lot of clay. And here's the CEC. And you might be thinking CEC. So that's the number of negative charges. And it's pretty low. If you have 10, a CEC of 10, it's pretty hard to grow stuff there unless you're just growing forest stuff. And that's what forests are adapted to. A garden You want around 20. And you might be saying, 20 what? 20 times 6 trillion negative charges per kilogram of dry soil. That's what the CEC is measuring. The number of negative charges per kilogram of dry soil. And they just lop off the 6 trillion because they don't want to say it over and over. But you can imagine 6 with 23 zeros, right? And a CEC that is 10 is 60 with 23 zeros behind it. And 20 has double that. And so the difference between a mollisol and this soil is like double the amount of cation exchange capacity as opposed to this soil. And what's really cool, there's all sorts of cool things, and I encourage you to like fool around and just play with this thing. Look at, here's where it is in Washington. This same soil can be found in all these locations, and a million other really cool things that you can look up. And I just highly recommend that. And we are at the end of our official time here, and we're just scratching the surface here, if pardon the expression, of what soil is and how it works and how it's formed. And I hope that some of that, just is so foundational that you will be able to notice things maybe that you might not have noticed before. And I highly recommend that you get the app, and wherever you are, you should be checking the soil type and fooling around and trying to learn about it. You will learn more by observing a soil and seeing what it's mapped as, and than you will any other way. And what I want you to do is I want you to see what the soil is mapped as, and then dig a hole and see if it's the same or not. And if it is or looks pretty much the same, you could probably trust this data. But a lot of you probably live in developments where they scraped off the good soil, brought in a bunch of crap, and you can't trust the data because the data doesn't know that it was scraped off, right? It's just what it was under natural conditions, what that soil would be mapped as. You might be wondering, how do they do that? They spent 100 years going out and looking at aerial photography, elevation, climate maps, geology maps, and making inferences and drawing those lines and then checking them. For 100 years, people did that. I'm a former president of the Oregon Society of Soil Scientists. The previous generation of the Oregon Society of Soil Scientists, that's what they did. They were mappers, soil mappers. 20th century is about mapping all the soils in the United States so that we could protect them, because it's about soil. Okay, so be happy to take some of your questions, either audio or however you want to do it.
James, fascinating stuff as always.
Oh, thanks.
Wanted in the chat to you, I put the address of the Grays Harbor County Fairgrounds. I'd like you to look up the soils there, because you're going to see huge, very rich, loamy soils up there.
I can't wait. Let's do this. So I am going to go. So where is the actual? I don't see the address in the chat. Oh, there it is. In Elma. Okay, here we go. Let's do this. Yeah, this will be fun. So now we can just screw around and have a good time. Let's see if I can get the Google Earth. And oops. Dang it. What happened there? Hold on. Hold the line. There it is. Copy. And paste. Okay. Let's go look at that. Okay, that looks more reasonable soil. Because it's not in a bog somewhere. So sometimes the soils are not mapped in very urban places, because they always have been urban places, and they said, why would we even spend our time mapping this, right? So that happens. But I doubt that that's the case here, because it's pretty small here, right? Let's see what it says. Okay, So what we've got, what we're showing here is a soil called Grand Mound. And then there's a Davis Creek soil, and there's a Hutula soil. And these are Vitrandic humizirapts. These are inceptisols that are formed from vitrified ejecta from volcanics, which are usually mean really nice soil, because volcanic soils are often fresh, aerosolized, like meaning already clay-sized particles that of molten lava that fell as ash, right? So let's look at it. So Grand Mound, it's a gravelly sandy loam. That's interesting. Okay, let's just see. And I got to go to Google Chrome to look it up here, and I got to change this to that. There. Can you see that? Grand Mound, right? Are we looking at the right thing here? So, yeah. So there it is. And that's just, you know, what's right there. Of course, most of it's covered up with pavement and stuff. And it has 10% organic matter, which is very high. I mean, 4% organic matter is really all you need. So don't just keep adding organic matter forever. Get a soil test. And once you get to 4% organic matter, you really don't need to add that much more. You just need to be growing cover crops to improve the soil structure, right? So let's look at the clay. So it's pretty sandy, it looks like to me, because I only see about 5% clay. So I'm guessing it has a high organic matter and a low amount of clay, but it probably has a pretty high CEC, because remember, organic matter has a higher CEC than clay. So look at 30 times 6 trillion trillion. I mean, that's why you're gardening. It's because you have a high CEC. And it's a pretty sandy soil. So it's a lot of organic matter. So it has a high CEC. And let's see what the sand is. Look at this. It's like 60% sand. I mean, it's like a dream soil. In fact, the student farm soil is similar to this, except it has a little more clay, and the particular kind of clay it has is really good, but it's still less than 20% clay. And the rest is sand and silt. So it's a sandy loam with a little bit of clay that's really good. And it only has about 3 or 4% organic matter. Here is the pH, at least in its native state, right? You've probably altered your pH, and you can see it's about 5.4 or something like that, which is a little low, right? You want it to be like 6.4. So in order to get your pH up, and especially with a lot of organic matter, you have to add quite a bit of lime. And I know that you probably have learned how to do those calculations, but essentially with a soil like that, just to change this pH by 1, you want to at least add 2 tons of lime per acre. Now, I know you don't have an acre there, right? You have some square footage. So all you do is take 4,000 pounds, which is 2 tons, and you divide it by 43,560. That's how many square feet are in an acre, 43,560. So you take 4,000. I'm just going to do it for you, because I can even do this. So, you know, it's doable. 4,000 divided by 43,560 is 0.09 pounds of lime per square foot, is the equivalent of 2 tons per acre. Let's say you have a 500 square foot garden. You take 0.09 at times 500, which would be 45 pounds. See how I did that? So now you can change the pH by 1, and then you want to get a test. And because it's so much organic matter, it can actually require more than that. But still, you can look at the BPH on your soil test and blah, blah, blah. And I'm sure you guys know about that, but I'm not going to spend a lot of time talking about that. I teach that. Here's the CEC. Did we look it up already? Yeah, 30, right? And there's the sketch. So there's that. There's another soil there And see how it says 85% grand mound and its geomorphic positions on terraces, and then there's 10%. What this means is probabilities of what soil is actually at that little dot right there. It's about 85% probability that's that. And Davis Creek is probably pretty similar soil. Dig a hole, look, 18 centimeters. I think this is in centimeters. And see if you notice at 63 centimeters, you start to see a change in this color. This one has 12% organic matter, even higher. It's got about the same, it's pretty similar soil. It's very sandy. It's got a lot more silt though. So this is probably, you said it was like a silty loam. Was that what you were saying?
It's the demo garden area.
Yeah. Is it silty loam? Have you textured it?
Yeah, very much so.
Yeah, it's probably more like this soil then, which has a very high CEC as well. Is that helpful? Yeah.
Other questions for James?
Here's where this stuff is, by the way.
We have a question here.
Since pH is logarithmic, moving from 5 to 6 is different from moving from 4 to 5. So how would you adjust your calculation?
Well, a soil test, and I'll show you, I have a slide for that. And that's a good question, and it is confusing to people. I'm going to get to, oh, dang it. I have a slide for that. At the very end of my slide, when you get a soil test, and it depends on where you go, like here's, A&L Western Agricultural Laboratories, which was recently bought out, so it's a little different now. But still, you'll see that the pH is given. Can you see where my cursor is 5.7. They also do a thing called the buffer pH. And so the pH is the pH of the soil. What the buffer pH is normalizing for the texture of the soil and the range that you're talking about, the logarithmic range. This buffer pH, it's unfortunate it's called a buffer pH, but what it does is you use this number to look up on a table where all those calculations have already been done to find out how much you need to add to change your pH from 5.7 to say 6.7 or whatever you want. Sometimes they'll give you that information in the fertility guide. Here it says 4,000. So 2 tons will do it in this one. That's what the guideline is giving you. But I'll show you something if you just bear with me. So if you can remember that the buffer pH is 6.6, I'm going to write it down because I can't expect you to remember everything for me. So let's say we have a 5.7 pH and the buffer pH, and it's sometimes called different things, but it's 2 numbers you'll get. One of them will be the pH and one will be this other number. And I happen to have a publication here on how you interpret liming, and it's there's a new publication on it, and you just look it up on find this quickly. Stay with me, stick with me. This will be worth it. It's a good question. I'm just going to look it up. So I'm going to share my screen so you can see what I'm doing, and I am going to look up liming soil OSU. I think there's a guide to it. fine line to raise. Well, they all have it, so we'll see what this publication has. Yeah, here we go. Can you see that? Yes. Looks like you can, yes. So this is a publication, and it kind of gives some pHs for various crops. But if you look down here, way down in here, this is kind of for different soil types. These are sandy soils going to clayier soils. So that's the old fashioned way, but here it is. So we had a soil that had a 5.7 pH and a buffer pH of 6.6. Look at, here's the buffer pH. It's called the SMP buffer sometimes. That's 6.6. In order to change our pH to from 5.7 to 6.4, see, this is the target that we want is 6.4. We use this line, we go all the way across, and we want to add 1 ton of lime per acre to change it. I know that doesn't match up with what the soil report said, but I don't know if they're using the SMP version or whatever. So that's, you just have to know what the buffer pH test that they're using is, so you can look that up. Now, they can do that for you, but it really is something you probably want to learn how to do if you're serious about farming. Does that help at all? It's kind of a long way, but I do have that information. I do teach this.
Other questions for James? James, a quick question with respect to soil testing. How frequently, do you really recommend it here in Western Washington, given our precipitation, et cetera, and soil conditions?
Excellent question. And make sure you're sampling correctly. What you're trying to do, just briefly, is you're trying to get a random yet representative sample, which is kind of like, what? Is it random or is it representative, right? So there's a little bit of a judgment call, and you want to sample soils that feel or look or are different topographical positions separate from each other. You don't want to blend them all together, but you do want to get a random sort of collection of samples, not much deeper than 6 inches if you're talking about gardening. But if you're doing berries, you want to go deeper, right? You want to know. And you blend that together and you send it in, and they'll give you the data. So just make sure you look up, there's a guide on that. You can, I'm sure that Washington State has how to sample soils, and you probably even cover it in your classes. Now, how often? Well, if it's just coming into production, you're going to want to do it to figure out your lime and see what you really need to be doing. And you might want to do it the next year again, just to kind of see if your liming actually did what you thought it was going to do to change your pH, or, and until you get that pH kind of dialed in, and at some point you won't have to worry about it too much, you might want to take a sample every year. I mean, just saying, if you have low pH soils and you're trying to correct for it, you got to know that you're successful in your calculation, or you're looking at the right guide, or the information. So you see what I mean? Once you get, and if you have low organic matter, you want to like build that up to 4% organic matter. I mean, that's kind of the goal, so again, if you're trying to get to a certain number in your organic matter, your lime, you might want to take it a few years in a row. Once you get that stuff kind of under control, you can probably back off to every other year or every 3 years. And what I do at the student farm is, it's a big enough farm that I don't sample everything every year, but I always am sampling some of it every year in a rotation, right? So I got 6 crops in a rotation. Every year I'm, sampling one of those blocks. And then by the time I have done all those blocks, it's been, 4, 5, 6 years since I've been there before. But I've been farming the same ground for 24 years. My organic matter is over 7%. My pH is dialed in. My P and K are off the charts, so I don't need to add any more manure or anything, because that's where you get your P and K, is if you put manure. And so now all I'm doing is adding a little feather meal on some of the crops that need extra nitrogen, but some of the crops I have more than enough nitrogen just coming out of my organic matter. I can calculate from having over 4% organic matter in my soil. I can calculate between 100 and 150 pounds of nitrogen being made available from that organic matter every year without having to add anything. So for spinach and lettuce and carrots and all that stuff, I don't have to add anything at this point, because I've been building up the organic matter levels to the point where they're just, leaking out nitrate every year. And there's enough of it that it's a lot. And for my tomatoes and my overwintering cauliflower, my winter squash, I might have to put on 50 or 100 pounds of plant available nitrogen in the form of feather meal. But my P and K is completely under control. I don't need any more. I'll never need any more. I'll be dead before my garden needs more P and K. And my lime score, my pH is, I'm in the 6, 8 to 7. And I'm good on that for a long time. So I can kind of ease off on my soil testing, because I've kind of, what a lot of people do in gardening and farming, especially organic farmers, is they get into this soil building phase and they never get out of it. And the thing is you, at some point, you're just in a soil maintenance phase. And it's hard because it takes a lot of energy, time, expense to get yourself geared up for a soil building phase. And then you're going to change your system, it takes a little bit of courage to do that.
So James, a question that pops up in the chat here is a common question that we get from folks at our plant clinics. They come up and ask, how do I grow a particular type of vegetable in my soil type, given where I live?
Well, I actually have a kind of a cool resource for that. It's an OSU resource, and I'd love to share it with you. Here, let's see if I can find it. And I actually know where it is, so promises won't take as long.
And while you're looking that up, James, you have to tell us again about cooking your chickens in compost pile.
Well, I did that as an experiment with students. The chickens, of course, were, had been butchered and properly cleaned and everything. The soil, the compost pile gets to 140 degrees. And we just took our chicken and we rubbed butter and salt and pepper the shit out of it and wrapped it up in a whole thing of aluminum foil and just put it down in the center, and came back in 24 hours and it was like falling off the bone. Perfect. So I'm just saying. And how did that happen? Where did that energy come from? In fact, where did all of the energy come? It comes from the sun. And what comes out of the tailpipe of your car? CO2, water vapor, heat, and ash. That's what gasoline is. What comes out of every breath you exhale? CO2, water vapor, heat, and ash left behind. What comes out of a compost pile? What comes out of a fire? Anyway, so yes, here's a resource, and it's called the Veggie Production Guides from OSU, and it's pretty good, and it's been updated recently. I think you can see this. I'm hoping. Let's see. Yeah, and it's just vegetable production guides and OSU. You can probably just do that and you'll find it. And it has all these crops. And you can just, here's one called corn baby. I guess it's baby corn. Celery, for instance. I don't know if you know this, but celery is a real heavy feeder. It requires as much nitrogen as growing winter squash. It's like 250 pounds of nitrogen per acre to grow that. And yet you be going, well, celery, but nothing else tastes like celery. And celery is awesome. And I grow it every year. And celeriac is amazing too. But look, let's see what it got here. It's got the different varieties. Muck soils are ideal. Whoa. That soil that we were looking at early on, that first one we looked at, high moisture hold capacity. Look at this. Look at the pH. It gives you a pH range. Here's how to grow it, transplant it. Here's fertilizers. There's a nutrient guide. Just so here, look at it. Says here 100 to 150 pounds of nitrogen for muck soils. And I think it's more for non-mucky soils. And it probably gives that. Here's the phosphorus and the potassium. But you want to make sure that it says between 175 and 200 pounds of phosphorus, P2O5. The thing is your soil has some P2O5 in it. And you can give you should see how much you actually need, because your soil might be providing almost all of that, for all you know, depending on the kinds of soil it is. And there's a way to do that. If we probably don't have time to go into that, but I would be happy to do kind of a nutrient analysis sort of talk for you sometimes, but sure wouldn't be as much fun. I'll tell you that, but it might be more informative. I don't know. So that's an answer, right? All that stuff. Pretty cool. I use this all the time. You know, it's a really cool guide. I got to show you this. The port, I just, mostly Oregon centric stuff here, but the Portland Nursery Veggie Guide. It's called a Veggie the Veggie Calendar. Super cool. Check this out. I use this. It's Pacific Northwest. It's a little, you'd have to adjust a little bit for your conditions based on what you know, but it kind of tells you what you should be starting indoors and when. And I'm sure you have things like this up there, but I love this one. So like it's March now, and see the little asterisk next to that? That means it's the ideal time is to start indoors as eggplants and peppers. And here's what we should be growing outdoors right now: chard and peas, and spinach seeds should be going in, and asparagus, arugula. I'm going to get mine going soon. And here's some starts that you could put out. I just put out broccoli starts last Thursday. And here's April. There's a lot of stuff to do in April, but you can sort of see this dark, shady area. That's for winter gardening. So you should be starting stuff outdoors, Brussels sprouts, broccoli, all this stuff for winter harvest. And it also gives you these really cool spacing guidelines and stuff like that. Love this thing. And I just put it on my wall, and I just look at it every week and say, God, what am I behind on now? Because I'm always behind on something. Because you can't keep it all in your head. I mean, I've been doing this for 24 years, growing this garden. I have a pretty good idea what's coming up next, but I always check a veggie guide like this to make sure I'm not, oh shit, I didn't start any of the basil yet. And it's like disaster,
James, this has been phenomenal.
Yeah, helpful.
Super, super stuff.
Great.
We thank you for, an incredibly entertaining and educational background. Cool. And this, of course, this explains why your class at OSU is one of the most successful in the undergraduate curriculum there.
Thank you. Really appreciate it. And I'm kind of in awe of your ability to organize such an amazing, like spatially kind of an amazing program you got here. I don't know how you did that, but it's excellent.
Well, we're scattered across 3,500 square miles here in our two counties, so we've got to figure out how to connect everybody.
It's really great. I would love to come up there, though. Come on.
You were here about 10 years ago.
I was. Where were we?
You were up in Cosmopolis.
It's
in Grays Harbor County, south of Aberdeen.
Oh, right, man. I would love to come back up there.
And of course, you got to explain how we can get your soil t-shirts so we can all become groupies.
Oh, God, thank you so much for reminding me. It's the most important part of my whole presentation. Is, would you please? Thank you.
Thank you very much.
Yeah, I have these shirts that I sell. Let's see if I can find it. Here they are. Actually, 100% of the profits of this shirt and I have them in ladies and gender neutral, or I guess they're all gender neutral, but different styles. And 100% of it goes to help me pay for my summer intern program, of which I have over 250 paid interns in the last 24 years, completely self-funded through the sale of fruit and veggies and these t-shirts. And you just go to soilforward.org. There it is, soilforward.org. And you can buy them. And I also have them in Klingon and in Vulcan. So you may know someone who might even know what that means. And if you know, you probably know the Klingons in your life, and you know the Vulcans in your life. So they all need soil. And I really appreciate you having me here today.
Thank you so much, James.
Okay.
So Sheila, I think we're ready for a break now.
I am. Thanks.